Good evening, all. So we have today our speaker of the first session, Dr. Manoj Kumar Gaur. Sir is working as a Dean Research and Professor in Mechanical Engineering Department and in charge at Chemical Engineering at Madhav Institute of Technology and Science, deemed to be University, Gwalior, India. He has made substantial contributions to the field of solar thermal energy, solar distillation, and heat and mass transfer applications. He possesses 23 years teaching experience of postgraduate and undergraduate classes. He has authored 3 books. More than 100 of his papers have been published in various international and national journals and conferences. He has guided 6 PhD students and 35 MTech dissertations. He is an active reviewer of various prestigious journals. He is a life member of the Indian Society for Technical Education, IET, and faculty advisor, Society of Automotive Engineers, India, MITS chapter. He had obtained PhD from Indian Institute of Technology, Delhi, and Master of Technology in Engineering Materials from Maulana Azad National Institute of Technology, Bhopal, Manit, in 2002. He secured 5th position in the university in his Bachelor of Engineering in Mechanical branch from Oriental Institute of Technology and Science, Bhopal, in 1999. So now I request Sir to start his session. Sir, please.
Thank you, Deepak ji. First of all, I am thankful to Dr. Rajesh Kumar Arya, principal of your institute, for giving me opportunity to deliver the lecture under the AICT ATAL Faculty Development Program on engineering the future of energy, AI, data science, and efficient power system for the climate resilience. So once again, I'm very much thankful. Now I will share my slides that I'm going to present. Is it visible to everyone?
Yes, sir, visible.
And my voice is clear to everyone?
Yes, sir.
Okay. So just I will go through the how the heat transfer analysis can be we can do for the solar thermal system, and how much we can save the CO2 that is a greenhouse gases while using the solar thermal systems. So first of all, we all say about the now everywhere the agenda is sustainable development agenda goals are there everywhere. You will find if you have been working some on dean position or somewhere else in your institute, the AICT and government is asking to what the sustainable goal which you are going to achieve in your institute, whether it is waste to energy conversion or you are purifying the water by some mechanism. So a lot of points are there which covers under the sustainable development goal. So when we talk about the sustainable development goal, it is an organization principle for meeting the human development goals, at the same time sustaining the ability of natural system to provide the natural resources and ecosystem services upon which the economy and society depends. Means if we have been harnessing our natural resources and somewhere we are using the natural resources and other things which are available and plenty in the earth, so we should have to maintain that it should not be used in abundant form. Also, we have to ensure that for the forthcoming generation, their needs can also be fulfilled. So we should not harness our society, not our ecosystem, as well as the natural resources. So in the meeting that the United Headquarters in 25 September to 27 September 2015, it has been decided there the 17 goals were decided and 169 target was there. The five, they have worked on the 5 Ps. There's a people, planet, prosperity, peace, and partnership. So if we look at all 5 Ps, they are comes under the 17 goals and 169 targets for the sustainable development goals. People, we talk about the people means it is related to we talk about the social aspects of the sustainable development goal. If we talk about the planet, we talk about the our environmental aspects of the sustainable goal development. If we talk about the prosperity, it means we talk about the economy and the economic aspect of the sustainable development. If we talk about the peace and partnership, that is the ethical and that is a collaborative sides of the sustainable goal development. If we say 17 goals, everybody should no poverty, zero hungers, everybody should have the clean water, everybody has the energy, everybody has the good education, quality education. These are all 17 agendas on which the global sustainable development department is working. So if we talk about what are the challenges, economic development challenges are there, human settlements are challenges, energy and climate is also challenge, water and waste, biodiversity and governance. If we talk, I will not go through all, but I will discuss about the energy and climate change only. So, if we talk about the goal of energy technology, we all everywhere you have listened that the goals of energy technology. So, for the what goals we have to set in our daily life or in our family or as a worker in our institute, reduce the use of fossil fuels and which are having the global warming potential or having produce the impact to our earth and society. That impact, it may be in the form of greenhouse gases, or which will be harmful to our planet as well as earth. So we have to reduce those things, like we have to reduce the use of polythenes. We have to reduce the use of conventional energy sources. So recycle the product which we have been using, that should be recyclable. Refuse use of the one single plastic. We have to refuse it. Responsibility. It is our responsibility to clean or to keep clean our planet as well as our society, and repair your whatever you have been using. It should be repairable. And lastly, renew, that we have to use the renewable energy sources for the needs of our energy requirements. So examples for some green energy technology, recycling, clean water, clean air and energy, all these are some examples for the green energy technologies. If we see about what is the scenario at the India, what the current scenario of power production in India from the various sources, it may from the central sector, private sector, and state sector, and considering the thermal, renewable, and nuclear, it comes around the 4,56,757 megawatt of the electricity installation capacity we have currently we have in India, out of which renewable, that is around 2 lakhs 5,520. That is the biggest data. And also, if we talk about the only, not if we break the renewable and from the solar systems, solar energy, that will be around 1 lakh 58,000 we have achieved around this year from the solar, wind, and small hydro. That is the current news, which was in which came in on 3rd of January. I think that will be also published in all over the Madhya Pradesh, that the 2000 year was the warmest year ever in last 2010 to 10 years. So that October, that was the highest temperature of the month recorded in last 123 years. October was the hottest month of the year 2024. So that the temperature, that is the average temperature, that is increased by 0.65. And all the sustainable goal agenda and all the climatic researchers, they have been working to how we can we should have to reduce the temperature, average temperature by 1.5 degree. So the researchers are working on that. So this is a trends for how the temperature is changing from 901 to 2024. It's increasing. That's the dotted line which is showing continuous increasing the average temperature of the every year. So this year, that was the hottest year in last 10 years, starting before this, the 2016 was the average increase in the temperature was 0.54 degree centigrade. If the temperature is going to be rise by 1.5 degree or 2 degree, the most of the cities, some parts of the Bombay also, there may be some parts will be having the water that will be come out from the sea level will be increases. And also the India has been working on increasing the how the clean energy can be increased. In last 5 years, there's an increment of 2026% took place. And moreover, the earlier the rate of the 1 unit of electricity was by the photovoltaic system was around 9 to 10 rupees per unit. Now it will be around 2 rupees 36 paisa for single unit. And also a lot of companies which have been working in Madhya Pradesh they have been developing the ultra and solar power plants in various parts of the Madhya Pradesh. Omkaleshwar, there is a floating type of power plant, photovoltaic power plant is already developed. And one is going to be developed is, in the Morena. They have been developing the solar park. Coming to the whatever the amount of the available solar energy in India, if we say if there is 250 and 300 J on the clear day, then the amount of the solar radiation, which varies from the 1600 to 2200 kilowatt hour per meter square. That is the annual average solar radiation which is available in India. That is 1600 to 2200 kilowatt hour per meter square. Generally, we take the reading from the solarimeter that will be come out from the watt per meter square. And if we take for the whole day, the average day time depends 5 to 6 at 5 to 6 we can take hour for the average solar insolation or solar radiation. And if we calculate this, if we multiply this by with the area which is available for the which is available in the India, that the amount of the energy potential which we have, that is around 6,000 billion gigawatt hour electricity per year, which with this potential we have in India. So coming to the what the zone which is available in India, that's the 5 zones are we consider divide India into 5 climatic zone: hot and dry, warm and humid, composite, moderate, and cold. If we look for the Madhya Pradesh and around the Punjab, Uttar Pradesh, and Chhattisgarh, it comes around the moderate climate, composite climate. That's the moderate climate is there because the this temperature is around 25 to that's a if we talk about the 25 to 30, that will be the moderate, and we will talk about the composite. Means any one of these comes when the 6 month more than do not fall within any one of these above categories, that is comes in the composite climate. And Madhya Pradesh and all Chhattisgarh, some part of Chhattisgarh, there is a Punjab, this comes in the composite climate zone. But the Rajasthan, it comes in the hot and dry because the humidity temperature is greater than 30 and humidity is less than 50%. So coming to the what are the solar thermal systems? We all know about the domestic hot water heating systems. Everybody knows solar desalination is to get the purifier water. Solar drying is there. Heating of room by the air, cooling by some vapor absorption refrigeration system. By using the solar radiation, these are all systems where we can use and harness the solar energies to use for our use. That may be the heating purpose or cooling purpose or to generate the electricity. There are two different systems. that can be utilized as that's a one from the photovoltaic system, other from the thermal system. From both the system, we can harness the energy from the sun. So two parts are there. There are two rooms. One for the we are getting the hot water by harnessing the solar energy. Another the part we have been using the hot water as well as we are using it for the heating of the room. We can use the radiator in the room and we can circulate the hot water. But somewhere directly we cannot use the water. We can use some heat exchanger where the brine water or saline water can use some salt may absorb the energy, and that salted water can be circulated to the room where we have to heat. So other system is solar cooking. It is also very important. Solar cooking in normal solar cooker is also there. Dish type solar cooker are there. In this type solar cooker, what we do, we generally concentrate the radiation to at the focal point of the dish, where we can put the items which have to be cooked. So coming to the solar power plant, if we talk about the solar power plant basically we harness the solar energy with the help of heliostat, and there may be the oil which can be heated oil can be circulated through the heat exchanger, where the water can absorb that energy and convert it into the water vapor. That can be used in the there's a turbine where the electric we can produce the electricity. Coming to my topic that I'm going to discuss, that is a now we are going to start with what we did in our MITS and during my research career, what I've been doing and what I did. Some parts which I have been going to present here. One is the solar distillation, on which I have produced one PhD. One of my student, he completed PhD under my guidance. One of the student he is doing, and I have also completed my PhD under this particularly solar distillation. So, what is the purpose why this desalination solar distillation is important? Because we talk about the area which is available on the earth on which the fresh water is available. It is around only 1%. We talk about the quality of the drinking water. So we say the most of the in India, most of the people, they are consuming the water which is having the TDS level around 500, more than 500. So 500 may be permissible, but some part of the India they have been using the TDS level. It is around 1000 ppm. So if we use this solar distillation technology and we use the solar energy, so we can convert the brackish water into the potable water. So other than that, in villages and somewhere less part of the country, it is very difficult to get the potable water. The people did the hard work to get the potable water. Even they have been using, it is not the good water, but it is brackish water they have been using for their daily use. And also, if we see in the past, there's Pune was having the zero water day, and also in water crisis is there in Bangalore also. Coming to the cost of the water, in India, there's a cost of the water is around 20 rupees per liter, but somewhere else it is more than 100 and 200 rupees per day. Norway is having the highest cost. Comes around 220 rupees per liter. So coming to the history of desalination, if we talk about the history of desalination, so first solar distillation that was developed, apparatus that was developed in De La Porta in 1589. What he did, he uses the earthen pot to get the essence of earthen leaf. That earthen leaf, the essence of the earthen leaf is used for the medicinal purpose. He took the inverted earthen pot and he used put the leaves inside it, and by getting the heat energy which is coming out from the sun, and the essence of the leaves that evaporates, and there's a evaporated part, that's a essence that will be collected through the beaker. And that's the first solar still that the patent was done by the Carlos Wilson in 1872. And India, Lakshadweep, and there is 7,500 meters square. They have developed in 93. They have developed a solar distillation plant, solar stills, and also past in 2020, the money Prime Minister Narendra Modi ji, he inaugurated the that's a solar desalination plants as well as the solar energy park also. That's a hybrid solar energy park. Uh, that's having the 30 gigawatt of the hybrid renewable energy park that can be able to develop 30 gigawatt of electricity. Also, the desalination is 10 crores liters per day. That the water can be purified by using the solar desalination plant. Coming to the principle of solar still, if we talk about the principle of solar still, so we talk about the solar still, the radiation which is coming out from this sun, there is a partly solar radiation will be absorbed by this glass surface. This is glass surface. Partly will be reflected again back to the atmosphere, and partly will be go inside the basin. That is particular. This area is called basin, where we can fill the water, and that water gets the energy which is coming out from the after the transmission of this glass. That energy will be that solar radiation which falls over the surface of the water. Here again, the water will absorb the radiation, and partly will be again transmitted to the liner of the solar still, and partly will be reflected there. We all know the glass having that is a quality which allow the short wavelength radiation to pass it, and it will not allow long wavelength radiation to go through it. Once the temperature, if the water gets heated from this, the radiation which emitted from this water will not go from this glass, and this total solar radiation will be trapped by this surface every hour, and hence the water gets heated and gets evaporated. There are three types of heat transfer which takes place from this water surface. That is evaporation from water surface, convection from water surface, radiation from water surface. These all kind of three heat transfer takes place from the water surface. There may be bottom losses from the bottom surface, that is the conduction losses and radiation. From the glass surface, the radiation, and also from inner glass to the outer glass, that will be the conduction, and convection from glass surface to the medium. All this heat transfer takes place from the solar distillation system. If we talk about the types of solar still, one is the passive solar still, and another is the active solar still. If we talk about the passive solar stills, means the heating of particular system. That the heating of this basin water is there inside the basin. The heating of water basin, heating of water of the basin only by the solar radiation which is coming out after the transmission of this glass. Heating, what we do, only the energy which is received by the water only by the solar radiation which is coming after the transmission of the glass. There is no additional system which is attached with this system to heat this water. This is only passive solar still, where the heat transfer within the water took place because of the free convection, because of the buoyancy, and that the heat transfer, that the water gets heated and heat transfer takes place. And that is a single slope, and this one is the double slope. Single slope is always kept, the surface of that glass cover should face towards the south. Why we took the system, our solar system, that should face the south? Because we are living in the northern hemisphere, and sun rises from the east and set in the west. So every day, a full day, the solar, our desalination system or solar still the glass of solar steel face the solar radiation. It should absorb the solar radiation. But in case of double slope, in the morning time, the portion which is in the east side, which will absorb the solar radiation largely as the days goes and sun goes after the 1 p.m. and before the rising, before setting in the west, the portion which is in the west direction, it will receive the solar radiation. So double slope is always kept facing towards east and west direction. And slope of this glass cover is equally important. Why we have this slope of the glass cover? It's 15 degree. Why not 30 degree? Why not 50 degree? That is very important. If we talk about the what should be the angle of this glass, it should be latitude plus minus 15 degree. So latitude of the place where we are putting this system, if our system has to work in the summer, it means latitude plus 15, summer latitude, winter latitude plus 15, and for the summer it should be latitude minus 15. So if we talk about the Delhi climatic condition, Delhi, it is around 30 degrees is the latitude, 32 minus 15, that is for the summer. For the summer, 15 degree will be better. If we have to check the good performance of a system, the system should perform better for all around the year. It should be kept at the latitude of the place. Always for the better performance of the system, we should keep our system at the latitude. But in your houses or somewhere in industrial buildings or government buildings, you will find the wrong angle of the photovoltaic system. Why they've been using this? 1 minute. अभी आराम जरा मुझे पानी देना बेटा. Why they have been kept the small angle, then the latitude, because of the they have to save the materials and cost of the material. They have to save the money, and nobody know about the what should be the angle. They install the photovoltaic system over their roof, but they don't know what should be the angle of their system. So it will difficult to understand why our system is not performing better. This particularly solar steel is, if we talk about both these two solar steel which I am showing you, that the one is active solar steel. Why this is active? I have just in previous slide I talked about passive solar steel. In what I did in that particular case, only the solar energy radiation which is coming after the transmission of the glass, of the transmittance of the glass, which I've been using to heat the water. In this case, solar radiation is also coming through the glass. Secondly, I've been using the energy of flat plate collector also. And the bottom side, that is the hybrid active solar. If we use the word hybrid, it means in same system there are two kinds of energy. One is thermal energy, which I have been using. Second one is the electrical energy. The PV panel is there. The electrical energy which I am getting, which will be utilized to run the pump. Pump is just below this panel. The pump is used to circulate the water through the flat plate collector and the basin of the solar steel. So what kind of energy in one single system? That's why this system is known as hybrid active. Active is there because I am using the additional energy of the flat plate collector, which I am adding to the water of the basin. I have already told about what kind of heat transfer which took place from the solar steel, that is the convective heat transfer, evaporative, and radiative heat transfer. That is from the water surface to the glass. How we can calculate that? There are the standard correlation which is given by the various researchers. Basically, we use the Dunkel's relation, which is given by the Dunkel's. This is the first scientist who developed the correlation for the solar still. That's the evaporate. We all interested. The researchers are interested in particularly evaporative heat transfer coefficient because it is responsible for the amount of the water which gets distilled, and that the convective heat transfer coefficient that we can calculate through the using the calculation of Grashof number and Prandtl number. That is the thermal conductivity of vapor, and that is the characteristic length. That characteristic length that we can calculate. How we can calculate? So most of the people, they don't know how we calculate the characteristic length of the, that is the water surface. Suppose after the water surface, this is the lower side length, that is the upper side. Suppose this is L1, this is L2, the LCR equal to L1 plus L2 by 2. That will be used while doing the calculation of solar still, because for every systems, rather using the value, constant value of C and N, if you have to get the accurate solution of your solution of your system, accurate experimental result, then you can calculate your own value of C and N by using the experimental data. Top loss, that's a top loss from, that is from the glass surface to the ambient air. That is a convective heat transfer coefficient. Convective heat transfer takes place from the glass surface to the ambient air, and radiative heat transfer takes place. These relations are also there, but sometimes most of the researchers, they generally do, because of the less heat transfer, less the value of heat transfer, most of the researchers, they use the correlation that is already given on the basis of the temperature. We can directly, if we put the value of the temperature, we can directly calculate the convective heat transfer coefficient, radiative heat transfer coefficient. Just we have to put the value of the glass, temperature of the glass. Coming to the bottom loss, if we talk about the bottom loss, there will be the convection from inner surface to the outer surface of the bottom, and from the convection from the bottom surface to the ambient. Also, side loss may be there from the solar still, but most of the cases we neglect the, when we write the assumptions, we write we should have to, I'm going to neglect the, neglecting the heat loss from sides of the side walls of the solar still. So after discussing all of these, what are the factors which influence the productivity of solar still? One is the water depth, because the most of the energy which is going to be absorbed by the water. Second one is the slope of glass cover, equally important, because we have to transmit the maximum amount of the solar radiation which is falling over the surface of the glass. Third one is the thermophysical property of the basin fluid. हमने जो brackish water use किया, whatever the brackish water which we have been using, the thermophysical property of that fluid is very important. Design of solar still is equally important, whether it is insulated, surface, bottom surface, side surface are insulated or not. That another system is there. If you have to understand the outer condition, so we can develop the inner solar cell. That I prepared this model to understand the actual condition of solar still at various temperature. That particular system, that's a constant temperature bath, where we can keep the temperature of this water constant by using this system, where we can set this temperature, say 35. We know the temperature, we start the temperature from range to 35 to 85. That for the passive solar still, there's a range is around 35 to 55 degrees centigrade. If we talk about the active solar still, it's range from 35 to 85 to 90. higher temperature may be achieved by using the active solar still. So we have to check the performance of our solar still by keeping this temperature of the this constant temperature bath for the 35 degree, next 5 degree, for after increasing the 5 degree, 40 means 45, for 50. We check what is the productivity of solar still at a given temperature. We keep is still stagnant air of the room. So various thermal models which are available, which are generally used for the calculation of various heat transfer properties of the solar still. Generally, uh, these models are, the first model is Dunkel, which is given for the passive solar still range. How we calculate the convective heat transfer coefficient? There is direct correlation is given by the Dunkel. He given the value of N and C and N. We generally we Grashof number and Prandtl number keep power N and C. So that is particularly HCW equal to, we have calculated that's KV into divided by L characteristic length C GRPR. So that particular, after the giving the some experimental data and finding out the correlation for the that's the value of C is 0.88, delta T which is which come out from the Grashof number, and N value is 0.3 up to the range of 55. That is for the range of 55 degree. So delta T, for the delta T, he gave the relation for delta T, TW, TCI, water temperature, inner glass surface temperature, partial pressure at the water temperature, partial pressure at the inner glass. Because here is the water, this is the glass, and we record the temperature at the inner surface. On the basis of inner surface, we calculate the partial pressure. There are formula is there, that the exponential relation is there to calculate the partial pressure. PW, that the water temperature. PW is the partial pressure at the water temperature. That's a constant value. Now we can calculate the value of HEW. HEW equal to, again, there's the correlations directly given. 0.163 HCW, PW minus PCI. Again, this is the partial pressure, ratio of partial pressure. So that that model is a very famous model, and every researcher use this model. Every researcher uses this model. Coming to the next model, which is chain model, he gave the relation for the range of Rayleigh number. Rayleigh number is a product of Grashof number and Prandtl number. For the given range, that is a 3.5 to 10 to the power 3 and 10 to the power 6. For the calculation of convective heat transfer coefficient, we can use the correlation, 0.2 Ra ki power 0.0 kV divided by xv. Here xv is the characteristic length. And again, this H, convective heat transfer coefficient, if we put the value of convective heat transfer coefficient into this relation, this value, if we put here, we can calculate the HE, and that HE will be again used to calculate the theoretical mass output or distillate output from the solar cell. Again, Adhikari, that he did the experiment in IIT Delhi under the controlled atmospheric condition, under that's a air conditioned room, and for the given value, he directly given the value for the what will be the distillate output for the given range of Grashof number. And for the particular range of Grashof number, he also defined the value of N 1.4 and 1.3. And based on this, the mass, that is the output of solar still can be calculated. And best model, that is the best fitted model, that is a Kumar and Tiwari, Professor G.M. Tiwari, professor in IIT Delhi, and Dr. Kumar, that is a Dr. Anil Kumar. He is professor in NIT Raipur. He developed very good relations to calculate the value of C and N. Everywhere we have been using the value of C and N in previous slide. That's the value of C and N. this particularly value of C and N. For this value, based on the experiment, Kumar and Tiwari developed the model. On the basis of regression analysis, we can calculate the value of N for a particular set of passive solar cell and active solar cell. We have to take the reading, and on the basis of reading, we can calculate that. But what I did in my what model, which theoretical model, which I developed to calculate the value of convective heat transfer coefficient, rather than keeping the value constant. Here, in every researcher, in the denominator, every researcher kept this value constant. This value, every researcher that kept this value constant. In I am showing in previous slide, that's a value every researcher, whether it is Dantal or Adhikari, Chain, every Jang, they have already uses this value constant. Rather than keeping this constant, I have kept this as a variable. This value is vary with the temperature. As the temperature increases, the value increases. The temperature goes down, it goes down. So all the parameters, whether it's a physical property, is a function of temperature that I have used to calculate the property, physical property, thermophysical property of the solar cell. And on the basis of that, I have calculated the value of C and N by using this regression analysis. Mathematical expression is used. And based on this, I have validated the results, a theoretical result with the experiment result. And after that, the result reported that the least result is reported by my model, which model I have used to calculate the value of yield. That's the distilled output, which is coming from the solar cell, that is around 10.7% by using my own model. But if I have been using the, after that, the least result given by the Kumar and Tiwari model, it is around 13%. But the Adhikari model gives the high 31%, and chain model gives the highest error, that is around 38%. So this is all over the entire range of the solar cell. That is from lower range to the higher range, around 85 to 90 degree. Higher range, there's a from passive range to the active range. That is the all validation range for the validation for the lower range to the higher range is a passive to active range. If I have to check the performance, if how my system will be perform, how the performance will be in Leh Ladakh, where the ambient temperature is lower. If we take it, what I did in the which I earlier I shown the that's the indoor simulation system. In that particular indoor simulation, what I did, that I have kept the ice cubes over the surface of this still. What I did, I have I have completely filled this space by the ice and thermocol. I have kept the thermocol over this and kept the most of this time kept the constant temperature around 4 degrees centigrade, and after that recorded the distillate output, and then I have compared my result with ice and without ice. How the performance goes to be increased, because I kept the ice over the surface. So convective heat transfer increases, evaporative heat transfer increases, but the radiative heat transfer goes down. So it means if the outer surface ambient air temperature is lower, because if we go in Leh Ladakh or in Srinagar or Manali or Rohtang Pass, the radiation is very good, but the ambient air temperature is very low. So in Leh Ladakh or in Manali, our solar distillation system, which performs here, will perform better in that climatic condition because of the ambient air. If we are lowering the surface of the glass cover, higher will be the evaporation over the glass surface. Validation, sorry. So coming to the hybrid active solar cell, if we talk about the hybrid active solar cell and we check the performance, thermal performance of our hybrid active solar system. I have already discussed about, I have already told in the previous slide that the hybrid active because the two kind of energy which is simultaneous, which at the same time, what the kind of energy we are getting, that's the electrical energy which is using to run the pump, and that the pump is just below the panel, and the thermal energy which we have been adding, the thermal energy which is harnessed by the plate collector. Inside the plate collector, the water is circulating from this basin water to the through this pipes and pump. Water just flow through this like this, and through this it goes to the basin. The temperature goes increases as its system is known as hybrid active solar cell. So for the if suppose this is one number of collector, here is one number of collector which is partially shaded. So what should be the optimum value of the partial flat plate collector? That we have optimized by using the experimental data and some theoretical data. On the basis of I have to optimize what should be the number of collector, partial collector will be better to have the higher performance of our solar cell. So if we talk about the just structure, what is the line diagram cut section of the our partially covered photovoltaic panel. This is covered with the cell. This is glass, and this particularly cell and glass plate just below the tube is there where the water is flowing, and we can develop the thermal modeling for that particular system. For this system, what TFO for the TFO we can calculate the we can develop. I have developed the equation. What is the what will be the TFO after 1 hour? Theoretical value I can calculate by using my model, my theoretical relation which I developed, and TFO2 that can be calculated. If we if we validate particular for the single flat plate collector, the intensity of solar radiation, which we all know the intensity is solar intensity that is increases from morning hours and increases till the 1 p.m. and goes down till the 5 p.m. There is a same structure everywhere. You will find same. There's a pattern everywhere in every research paper. You will find that the solar intensity, solar radiation. If we draw the curve of solar intensity throughout the day, it goes increases and then goes down. 1 p.m. it most of the time 1 to 1.5, 1 to 1.5 means 1 p.m. or in between 1 and 2 p.m. the higher solar intensity can be achieved. But the temperature, if we see the pattern of the temperatures, temperature is somewhere we achieve the higher value of the temperature in 3 p.m. Why this happens in every research paper, you will see why it happens, because at the 3 p.m. The both the diffuse and direct radiation, that both the radiations plays the major role. The diffuse radiation, which is around the 3 p.m. becomes more, and that plays the important role by increasing the ambient temperature. So reflected radiation, because of the higher value of the diffuse radiation at the 3 p.m., the higher value of the ambient temperature is recorded at 3 p.m. So if we see about the hourly variation of basin liner temperature and TW water temperature, inner glass temperature and outer glass temperature, it will be achieved that the higher value of the temperature will be achieved by the basin liner. If we validate this system for the mass of the water, there's a 5 centimeter water depth at the solar still, and mass flow rate through the pump, that is around 0.055 kg per second, and number of collector is 2. If we calculate it the same pattern, higher value, that's the higher value which will be achieved by the around 80 to 85 degree higher value will be achieved at the basin line temperature. Hourly variation of yield, if we record the value of the yield. So yield will be higher, will be at 2 p.m. And we record this distillate output for the 24 hours. It starts from the morning 8 to we do the experiment till the morning 7 p.m. So 7 a.m. and record the whole value. So higher value will be distillate output will be around 1 p.m. Around 2 p.m. because at the around the 2 p.m. higher value of water temperature as well as the higher value of the basin liner temperature, and also at 1 p.m. we achieve the higher value of the intensity of solar radiation. If we optimize, if we see about the yield, if we increase the number of collector, so the daily yield increases, but the daily efficiency decreases. As the area of the 8 collector going to be increased, the loss of the in same amount, the loss also increases from the flat plate collector. But at the same time, the productivity is not also the increases so high as the heat loss from the flat plate collector. So the efficiency, daily efficiency goes down. If we increase the number of collector, for the particularly 50 kg of mass, the daily efficiency, that is the thermal efficiency, that the mass output divided by the input, that the amount of the energy that which is be received from the solar cell, is the mass of the solar cell multiplied by the latent heat. If we divide it by the radiation which falls into area, falls over the surface of the glass, then we have the daily efficiency. Daily efficiency over, if we combine together, if we sum the whole mass output, hourly mass output, and divided by the total intensity which is received by the glass surface, then we will get the daily efficiency. Also, the daily yield which goes down if we increase the mass of the water, because the what water will do, it will absorb the energy rather than it evaporate. It stores the energy. First, it stores the energy. So 50 mass the daily yield. That's a daily yield. If we increase the mass of the water in the basin, if we use a 50 kg and goes to the 200 kg, distillate output, that's the daily yield, which is goes decreases, and also daily efficiency goes decreases. So what should be the base on which we should have to optimize our system? So on the basis of exergy, we optimize our system. That if we see the exergy, if we see about the 50 kg, then 4 number of collector will be better. And if we talk about the 100 kg, 6 number of collector better, 6 number of collectors will be better. And similarly for 150 kg mass, on the basis of exergy, we can optimize our system. If we validate for our hourly yield, so that's a correlation coefficient comes around the 0.99. So it gives whatever the model which I developed for the calculating the value of hourly yield. That's which gives a closer result with the experimental. So these are all for cumulative result for the what amount of the daily yield which we can receive if 50 kg of water, 100 kg and 150 and 200 kg water used in the solar cell basin. So if we use the nanoparticles, how the nanoparticle affect the productivity? I have already told in the previous slide that the thermophysical property is equally important and equally affect the performance of solar cell. So if any way by which either we increase the temperature of water or increase the thermophysical property of the basin water, it improves the productivity of solar cell. We have in MITS, we have the solar cell. There's a different slope. Latitude of the Gwalior is 26, latitude plus 15, and once again latitude and latitude minus 51 degree. So we have lot of system in our MITS. My researchers they've been already working over that. This solar cell we developed in MITS and did the experiment preparation of the nanofluids. We have prepared the nanofluids in our laboratory. Very important thing is the concentration. Very important. What concentration of nanoparticle is important to get the performance of the solar cell. Second one is how to make your nanoparticle hydrophilic. So for that system, sonication effect, magnetic stellar, what things we will use to make it the hydrophilic with the water. So which concentration is better? We prepare the particularly uh, uh, solution and keep it for 24 hours and check which solution is stable. So in our case, in my case, it is observed that 0.05% concentration is better for the uh, particularly water and nanoparticles. And we have also calculated the thermal conductivity of the water as well as the nanofluids, that is the nanofluids copper oxide and zinc oxide. For the both for whole day, we have considered the thermal conductivity is the changes with the temperature of water. So considering the recorded the temperature of water, water absorbs the solar radiation, then we have calculated the value of K. So it is reported that there is increment of the thermal conductivity by 10% in the copper oxide and 3.75% the zinc oxide. That has been reported and calculated in our case, in my case. And if we considering all result, what the results, so why we kept this is a generally figure which is showing if we see the position of sun in the summer, that is a 21. So we want that the radiation should be fall perpendicular to this surface. So we have to reduce the angle. If that's the if we take the performance of 21st March and 21st September, that should be on the latitude. Latitude of place will be the better to have the performance better. If we go in the December on 21st December, the 41 degree at the 41 degree of Gwalior, the system solar system which capped at 41 degree, which received the highest solar radiation. So we have recorded the value of convective heat transfer coefficient, evaporative heat transfer coefficient for the various depth of the water in the basin at the 41 degree angle. That's the for that experiment which we did in the winter. That is at the angle of 41 degrees centigrade. It is observed that the water depth, the maximum temperature is achieved by the water at 55 degrees centigrade at the 4 centimeter water depth. So if we are using the nanoparticles, copper oxide, whether it's zinc oxide, so we have to keep the water depth 5 centimeter, 4 centimeter. It will give the better output of the water. So similarly, if the water output is higher for the that's the 4 centimeter depth. Similarly, we have recorded the pattern of the convective heat transfer coefficient, evaporative heat transfer coefficient, radiative heat transfer coefficient. Higher value is achieved with the nanoparticle, which is copper oxide. If we are using the copper oxide as a nanoparticles and a nanofluid we are using, which is having the copper oxide particle, which gives the better performance. We have the higher value of the convective heat transfer coefficient, higher value of evaporative heat transfer coefficient, then the normal cases as well as the with the nanoparticle of zinc oxide. So copper oxide gives the better results. And again, we have checked this for the 26 degree centigrade also. No, sorry, 26 degree tilt angle also we have recorded. Same we have reported. That's a higher value. We have also calculated the value of the convective heat transfer coefficient for basin liner to the water. Higher value of convective heat transfer coefficient is achieved. That is for the 41 degree angle and 4 centimeter depth with copper oxide particles. that we have reported. All we did experimentally and recorded and published number of papers on this. And if we go to the CO2 analysis, I have also did the cost analysis and CO2 analysis. So coming to the, because of the time, next the speaker is going to be wait. So if we consider the selling price 10 rupees, 15 rupees and 20 rupees, and if we check the what will be the payback time, that's the if we consider the annual productivity calculated, we have already calculated combined for 15 years, consider it for 15 years. And if we consider selling price 10 rupees, 15 rupees, then payback period for copper oxide will be around 1.69 years. And if we consider if we sell it for 15 rupees, that will be 1.09 years. So that we have calculated based on the embodied energy and all kind of energy we have calculated. All costs we have considered, annual cost and various costs that we have we have tabulated in this form and recorded the what will be the payback time for the solar steel with zinc oxide nanoparticles and copper oxide particles. If we talk about what the CO2 mitigation, that will be how much the greenhouse gas that we can save by using this solar steel, considering for lifetime span of 15 years, that 1.5, we always, most of the research you will find that they multiply 1.58. That's the amount of the amount of the greenhouse gases that is emitted by 1 unit of electricity which is generated by the coal. If we are generating the electricity by coal, then the amount of the CO2 which will be emitted, or CO2, or rather we can say the greenhouse gases which is emitted will be that amount will be 1.5 kg, 1.58 kg. So if we calculate and that the what amount of the CO2 which we are going to save, that will be around 5.97 for the conventional. If we have been using the zinc oxide, it will be around 7.75. If we have been using the copper oxide, it will be around 12.32 ton of CO2. And if we talk about the carbon credit, if we considering the cost of the one credit for the 2021, the highest will be cost in terms of rupees, which will be 13,557.95 rupees in 15 years we can save. We can earn by using the carbon credit, by selling the carbon credit. So this is similarly pattern if we use the PCM. In PCM, what happens in the daytime, the productivity is little less as compared to the conventional solar cell. But after the 3 to 4 p.m., the productivity goes increase because the PCM absorb the energy, and as the little less solar radiation is coming out from the sun, at that time that the energy will be released by the PCM. So, but if we check the overall performance of solar cell productivity, if we use the PCM, the productivity of solar cell increases. If we talk about the dryer, so second thermal system, which I am going to discuss, is the solar dryer. Solar dryer is very important because particularly increasing population, food demand of food is also increasing. Or we have also reduced the post harvesting losses, because if we do in open sun drying, there is losses, and maybe the contamination of crops is there. There may be the dust over the crop. The possibility is there. Color, texture, and everything. There may be possibility that will contaminate the crop of the which we are going to dry. So solar drying system, particularly controlled drying, uncontrolled drying. We talk about the uncontrolled, that is the open sun drying. We talk about the controlled drying, that is the active drying, and passive drying. In passive drying, only the buoyancy effect, that heat transfer takes place because of the free convection. There is a buoyancy effect. But in active drying, we use the fan to circulate the air throughout from the dryer, which pass through the crop and the moisture gets evaporated from the surface of the crop. That the all these, particularly direct dryer, indirect dryer, and mixed mode dryer. In direct dryer, we just kept the crop just inside the dryer, and the solar radiation which falls over the glass or some canopy cover transmitted and goes to the it goes to the crop, where the moisture get evaporated from the surface of crop. And indirect type dryer, where we can use the air which gets heated from the flat plate collector, that will be circulated through the some closed area where we put the crop. And third one is the mixed mode, where we can use the air heater as well as the direct dryer on which the radiation falls. That dryer, that is a hybrid dryer greenhouse, which we developed in MITS. Also, other types of dryer, most of the some people have been working. They've been using the burners also. The burner, they can use the gas flame. So there are a number of ample number of dryers that most of the research did develop and did the experiment. But I will talk about the dryer which I developed. That is the hybrid active solar dryer. That is the hybrid active solar, which we developed. That is developed in MITS, which I developed. This particular material is polycarbonate sheet. That's a durable, density is more, and also the heat loss. Heat loss is less as compared to the glass. Also the plastic sheet. So it gives a better performance. That's why we have chosen this polycarbonate sheet for the greenhouse dryer. This that particularly greenhouse light, particularly the surface is facing towards south, because this solar panel that generates the electricity, electricity can be utilized to run this fan. And this fan, why? Because this fan is we are using this fan to circulate the air through the through the bed of the crop. This particularly bed is there. We put the crop over that particular bed, and that crop dried, because this particular system is applicable for the hygroscopic crop. If we talk about hygroscopic crop, means there's two type of moisture. There's bounded moisture and unbounded moisture. The bounded moisture is basically in the roots of the crop, because of the capillary which possesses by the most of the crop. So this particular system dried the products in less time as compared to the oil dryer, which earlier developed. I have also got the patent for the particular this system. So all instrument we have to measuring the velocity of air, thermocouples, hygrometer to humidity measurement, solarimeter to measure the solar radiation, data logger to record the global radiation, wind speed, wind direction, everything. We have data logger. And most some crops which dried in this particularly dryer, there's a bottleneck, bottle gourd, and tomato and ginger. We've dried in our dryer, and developed the correlation also. This particularly correlation which developed by my student, that's Pushpendra Singh, and finding this particularly correlations give the better drying rate as compared to the all developed by the all other researchers. These are all correlations for the drying rate, which is given by the researchers. So we have calculated the heat transfer coefficient, drying rate. We have for the drying tomato, ginger, and all everywhere we have reported our system gives the less takes the less time to dry the product as compared to the other dryer or so open sun drying. So any questions, query related to my presentation, I am happy to answer. So please.
If anyone has any question, you can raise your hand. Anyone has any question?
Or you may, if you have any query, further, those who have been working on particular solar thermal systems like solar dryer, greenhouse, solar water heater, solar cooker, solar distillation, they may directly put the mail to me. I will try to answer and solve their problem which they have been facing while doing the experiment or while doing their research work. I will try to solve.
Sir, have you any slide which shows your contact details?
My contact details is also available on website. I've been working in this MIT's Madhav Institute of Science and Technology. Already contact details are there. Email ID and everything is there.
Okay.
Complete biodata is there.
Okay. So I don't think there is any question to any audience. So, sir, thank you very much, sir. Your insightful remarks and expert analysis were truly enlightening, and we appreciate the time and effort you took to share your knowledge with us. Thank you very much, sir.
Thank you, Rajesh sir. Because most of the time I never answer. Sometimes I never answered because of some issues that took place with
No
me.
problem. No
You
problem.
have asked some problem. I asked to send some data. But finally, I sent it all data to you.
Yes, sir.
Thank you,
No.
Rajesh Arya sir, for giving me the opportunity to deliver the lecture
Thank you, sir.
under the ATAL courses.
Yes,
Hopefully, the lecture will be helpful to the
yes, sir.
participants.
It will really be helpful for all the participants. Sir, so once again, from all the audience, thank you, sir.